Welcome to Catalyst Grid. My name is Kingsley Imufua, lead scheduler with DC Nordics. Today, we are building the machine at Hyperscale. This is Series 2, Episode 7, 132 kV and 33 kV GIS, the FULCRUM campus substation. In Series 1, Episode 10, we covered the full power architecture of Iron Gate, 33 kV intake, GIS at 33 kV, 7.5 MVA transformers, AIS at 11 kV distribution. This established our baseline for industrial power design. If you haven't watched Series 1, I'd highly recommend starting there, because this episode builds on every concept established in that one. At FULCRUM, we aren't just scaling, we are stepping up every single metric. The intake is 132 kV, not 33 kV. The primary transformers are 60 MVA, not 7.5 MVA. And the 11 kV distribution ring feeds an entire campus, not a single building. This is hyperscale engineering in action. Let's break down the FULCRUM power architecture. This blueprint shows how we move massive amounts of energy across the campus, from the grid intake to the data hall floor. It starts at the bulk supply point, or BSP. We take 132 kV grid intake and step it down to 33 kV via two massive 60 megavolt ampere auto transformers. These dual incoming feeds provide the redundancy required for a campus of this scale. The 33 kV level serves as our campus distribution ring. It connects the BSP to the on-site substation compound and then distributes power to all four data halls simultaneously, ensuring balanced load sharing. At the hall level, we step down to 11 kV. Each hall has four 15 MVA transformers and its own dedicated generator connection point. This modularity ensures that each hall can operate independently from its neighbors. Finally, 400 VLV powers the UPS and cooling infrastructure. For our AI-ready halls, DH3 and DH4, we utilize 400 V DC feeds. This bypasses the AC to DC conversion at the rack level, maximizing efficiency for dense GPU workloads. The FULCRUM on-site 33 kV compound is the heart of campus power distribution. It receives 33 kV from the BSP, distributes it around the ring, and provides the switching and protection for each hall group. The 33 kV incoming switchgear is 100% SF6-free GIS, featuring a double busbar arrangement. A bus coupler provides the operational flexibility we need to maintain power during maintenance or equipment upgrades. Each hall group is served by 8 15 MVA transformers. We've selected cast resin dry type units. Because they are indoor rated, we eliminate the complex oil bund requirements at the hall level, simplifying our facility design. Power is delivered via 4 outgoing circuit breakers in a ring topology. This means any single section of the ring can be isolated for maintenance without loss of supply to any of the other data halls. Safety and protection are paramount. We've implemented zone-selective interlocking across all 33 kV panels, bus zone protection with differential relays and arc flash sensors strategically placed on all bus bars. We utilize numerical relays with IEC 61850 Goose messaging. This digital substation standard enables peer-to-peer protection without hardwired pilot cables. In a conventional substation, every signal requires a physical copper cable. In an IEC 61850 substation, it is all done over Ethernet. This doesn't just reduce copper, it allows us to change our entire protection scheme through software configuration. Now, let's look at the giants of the bulk supply point. The two primary 132 kV to 33 kV auto transformers are each rated at 60 megavolt amperes. For context, that is 8 times the capacity of our Iron Gate transformers. Each transformer weighs approximately 200 tons. Delivery requires specialist abnormal load haulage, route surveys, police escort, road closures, and a crane rated for a 220-ton pick to position them. These are oil-filled ONUN and ONAF auto transformers. They provide 60 MVA under natural cooling, but can step up to 75 MVA when the forced air fans are active. This cooling flexibility is vital for managing peak campus loads. The vector group is Wynauto, featuring a common neutral. They also include on-load tap changers with a 15% voltage adjustment range, which are motorized and remotely operated from the BSP control room. Environmental safety is built in. Each oil bund is sized for 110% of the total oil volume. That is approximately 35,000 liters per unit. We conduct quarterly inspections to ensure total containment integrity. Before commissioning, every unit undergoes a rigorous testing scope, including ratio, impedance, and a full impulse test at 132 kV. Protection is supplemented by Buchholz relays and high-impedance differential protection schemes. Episode 3 introduced the concept of SF6 free switchgear. Now we look at what it actually means in practice on a delivery program with a supplier and during site execution. FULCRUM's 33 kV GIS uses G-cubed gas. This proprietary mixture of fluoronitrile and CO2 has a global warming potential of 1, which is over 99% lower than traditional SF6. It is a major step toward our net zero goals. Supply chain management is key. Only a few manufacturers offer this at 33 kV. We placed orders at stage 2 design to secure manufacturing slots against a 44-week lead time. Handling G-cubed gas requires non-interchangeable equipment and specific certification for all commissioning engineers. We've included this specialized training directly in our integrated commissioning plan. Our maintenance schedule includes annual gas pressure checks and specific topping up procedures. We've also updated our site emergency procedures to reflect the unique toxicity profile and PPE requirements for G-cubed gas. This 100% SF6 free commitment is more than just good practice. It is a cloud core contractual requirement and a DBFO lender covenant that we must demonstrate across the entire campus. From the 33 kV compound, each data hall group receives its own dedicated feeder, highlighting the massive scale difference from our previous projects. At FULCRUM, we have 4 independent 11 kV bus bars. This ensures that an electrical fault in one hall cannot propagate to the others. Our campus uptime is protected by physical and electrical isolation at every distribution stage. Generators at FULCRUM are rated at 11 kV output. By generating at distribution voltage, we eliminate the need for step-up transformers, reduce cable losses, and allow for much longer cable runs of up to 300 meters between the yard and the halls. Today's series signal, the digital substation, eliminates pilot cables, but it requires an understanding of cybersecurity for network-connected relays. Specify these requirements in the design phase, not during commissioning. In Episode 8, we look at 20 generators running in parallel. We'll cover generator yard design, paralleling philosophy, and the complex AMF logic required to sequence 20 machines simultaneously. Thank you for joining me on this deep dive into the FULCRUM substation. Building these machines requires precision, technical depth, and a vision for the future of infrastructure. I am Kingsley Imufua. Don't forget to subscribe, like, share, and comment below. Your engagement helps us build a better technical community for data center engineers. I'll see you in the next episode. Thank you for watching Catalyst Grid, building the machine at Hyperscale. Goodbye for now.